And I'll now take any questions that might have come in. So where is the ejector in the system located? So I'm going to bug Josh again for a close-up. So the ejector block on our system, it's over on the left side of the unit. This system was likely retrofitted with it, and that was the best place for it. But this is our ejector block here, and it is between the gas cooler and the entry into the flash tank. And then in parallel with this is our high pressure valve up here. We come around the front here. This is our high pressure valve. One thing I'll note, I mentioned earlier that you don't have to have both of them. There is some benefit to having both. In a low ambient condition on an ejector block, they're not equal stages through the different nozzles and ejectors, but you're only going to get maybe a combination of 15, 16 steps from the ejector block. Here you got 2,500 steps on the high pressure valve. So for low ambient, it does kind of make sense to have the high resolution of the stepper valve. And then when you get above a certain ambient, move over to try and get your Venturi effect, pull the trigger on the pressure washer wand, pull that load up to your parallel compression temperatures. I hope that answers the question. What determines when parallel compression is turned on and off? So what happens with the parallel compression? We've got I think we're okay without a close-up, but we've got a valve here, which is our receiver valve. We tell it in the software, if you look for the settings for parallel compression, there's not really an area. It's in the receiver valve settings. And you basically tell it, start the IT compressors. We call these IT for intermediate temp. There's low temp, medium temp, and then intermediate temp, which sounds better than high temp, I guess is why they chose intermediate. But you set in the software, I want at 40% receiver valve opening position, I want to turn on parallel compression. The way you turn on parallel compression is simply closing the receiver valve, which forces the load to go that way. So if you think about the receiver valve is normally open, parallel compression set point is set to flash tank pressure. So there's no reason for any pressure to make its way to the suction side of the parallel compressors to make them turn on. So we cause that pressure to rise by closing the receiver valve, which forces pressure to build, which will turn on your parallel compressors. And you get to set that how you want, when you want it to turn on within the software. So our next question is, how are the users controlling high pressure valve as a backup when the ejector block is utilized? I'm going to be honest with you, I haven't dug into that. It just came to light recently that most people put both valves. I've seen on this particular unit it doing what I described earlier in cooler ambience, that it's kind of taken over with the high pressure valve, and then at a certain point, the honest answer is we've got settings that determine that, but if I tried to tell you what they were at this moment, I'd be giving you a hip shot, which I don't want to do. I'm going to respond to all of these questions, and I'll put a better answer in it for you. So we have another question. What risk of bleed by is there when both the high pressure valve and ejector block are piped into the system? I mean, bleed by, we're really kind of looking at, I guess that question would determine if you're using the high pressure valve, maybe you're kind of partially feeding one or the other. What really happens is you'll switch from one to the other. Like either you'll have if you had all the solenoid coils burn out on the ejector block, pressure's going to rise to a certain point and the high pressure valve is going to take over as a safety backup. So you're typically not going to have the high pressure valve doing its thing, with the gas cooler outlet temp and the COP line in conjunction with the ejectors. You're going to have one or the other, but you can set it up to where you get below a certain ambient, you move to the high pressure, you get above that, that setting that kicked on the high pressure valve, you'll move back to ejector so you can start working on the Venturi effect and the lift for medium temp suction gas return. And then if you have both defined in the pack controller, it will by default use the high pressure valve as a safety backup should something happen to the ejector solenoids. Let's see, we have a question. Are the ejector nozzles able to modulate to adapt to load changes, or is it an on-off operation only? It's on-off operation only. I think it pressures that high with the small size of the components. It'd be really tricky to get a stepper type situation there, or to even pulse it. They're not even steps. Like the block we have here as an example has 6 cylinders for ejectors. It wouldn't be, let's pretend if there were 5 of them, it wouldn't be 20%, 20% across the board. It's set up more like 5%, 12%, 17%, so you can build different steps, but it is very limited compared to the 2,500 steps you would see on a stepper valve. So someone asked earlier about, is the oil system different? So the first thing to note before we start going through slides, if we can get the unit view. So we have over here, and I don't think we need a close-up, Josh. We don't need it. We've got an oil separator over here, like a large Pringles can that we saw earlier. And then that dumps into this fairly large oil reservoir. One thing to note on the reservoir, you don't want to have 1,300 pounds in the oil separator being what feeds the compressors, 900 pounds pressure drop across your oil solenoids. So this oil reservoir is actually vented at flash tank pressure. So it's got a line that goes to the flash tank to stay at the same pressure. So in our example, this is at 520 pounds pressure at all times because there's a line going over to the flash tank. So if you think about that venting over there, there's actually a little bit of load coming from that dumps into that medium temp suction that we kind of don't show, but there is a little bit going over there as well. There's 3 control methods in our pack controller. The first one would be a system where this reservoir has just one switch, which is a high level switch. So all the control is going to be done based in and around the level of oil in your oil reservoir. So on a system with a single switch, it's going to be a high level switch. And basically that's going to tell you that switch trips, you know that the oil reservoir is full. So we're going to activate what we call an emptying sequence. So that trips, and then we start pulsing the oil solenoid with a solid state relay output. And on the pack controller, there's two of the relays are solid state. And there's a sequence it runs through, which we'll look at in a little while, but it's going to pulse that valve on and off a given number of times in a given time period. And then once it runs through that emptying sequence, it'll stop. And then you'll just wait until the next time the high pressure switch is tripped. You'll run through the emptying sequence again, and you just do that in perpetuity. The second, which I think is kind of a belt and suspenders approach that I kind of like the best, is where you have both a maximum level and a minimum level. And you hit the maximum level, you start the emptying sequence, and you pulse the valve continuously over time until the bottom switch activates to let you know you've emptied the oil reservoir. On the first setup, you could theoretically be just emptying it a little. You're not really going to know it because you would just hit the one switch, run through the sequence, and hope that it emptied it. You have both switches, you'll guarantee that you've emptied the reservoir. And then the third option, which is more common than you'd realize, is there's no level switch. So basically it's all done on timing, and it actually works pretty well. So what we would do in that scenario, let me let these pull up here. We would define that we have one separator, and then we would go in and physically jump a high level switch with like a wire jumper on an input that stays in there forever. And that initiates our emptying sequence at all times. And then you can define from there how often you want it to empty. So in this scenario, if you follow the little laser here, we're telling it when the high level switch activates, run through a full sequence. And that full sequence here, we've got 1 minute repeat time. And then basically the period time is 4 minutes, 240 seconds. And then a nominal time of opening. What all of that adds up to is when the high level switch is closed, that I want to open the pulse valve. I want to open the valve for 15 seconds every 4 minutes. And then I'm going to wait 1 minute. I'm going to do that again. And I'm just going to do that forever because remember, we physically wired in a jumper. So every 5 minutes, I'm going to open the dump solenoid for 15 seconds. And I just do that forever. That's a pretty effective means. And if you were dealing with that on a startup, having oil issues, either getting oil, if you were starving for oil, you might consider adjusting this nominal opening time, increase that a little so that you're trying to get more oil out of the separator. So those are kind of our 3 options: high level switch only, high and low level switch, and then timing only. I hope that answers your question about the oil. So we have a question: how would a CO2 system work in sub-zero ambient temperatures? I got that one yesterday. It's a really good question. If you think back to when we talked about the high pressure valve, you give it a minimum range and a maximum range. So regardless of what temperatures the gas cooler is seeing, if you tell it the minimum is 600 pounds, whatever temperature that equates to, let's say that's 50 degrees-ish. If you set that as the minimum, it's going to close itself off to build the pressure in the gas cooler to not be above your minimum setting. So regardless of ambient, you're still going to have medium temp compressors discharging heat to the gas cooler. Let's say it's a block of ice up there. You're still going to be moving mass flow, able to build pressure because these are pumps. They move pressure. So your high pressure valve is going to limit the low end of a system, much like a drop leg regulator or your flood valve would do on an HFC system. Excuse me, how does the controller determine capacity required from ejectors? So it's basically defined. That's a great question. I had never had anyone ask that. So it's defined within the controller, not unlike condenser fan banks. You select a model for the injector. So I think the one on the table over here is an HP high pressure 1875. When you select that model, it knows what ejectors go in that, and it'll predefine the various capacities of the ejector blocks based on the model entered in the software. So in theory, you could have some control issues with an ejector block. Might want to check the model on the ejector block itself and verify that's what's defined in the pack controller. So we say, how many different CO2 racks setup are there? So there's actually a lot. So if you just take these three options, standard transcritical CO2, which typically would be booster and include low temp. So there's transcritical booster, then there's that same setup with parallel compression, and then again with ejectors that would also include parallel compression. But that's all on the transcritical side. You'll also have liquid overfeed CO2, pump CO2 systems. There's systems that use CO2 on the bottom side with HFC on the top side or ammonia on the top side. There's a myriad of different ways to do this. My personal opinion, what I've seen successful in the field for contractors to easily adapt to, and as well, much less expensive, some of the liquid vapor separators on the liquid overfeed systems, you know, they're extremely expensive. I think transcritical is probably what you'll see as the majority of the market moving forward. Efficiency greater than HFC systems. So I have a question about efficiency of CO2 versus HFC, as well as initial cost, refrigerant costs, concerned about oxidation. So yeah, these are all, those are very fair questions. I had the pleasure of hosting a group of store operators yesterday, and they have a very different take on CO2 adoption than that I myself would have about it. But as far as efficiency of the system, CO2 is a much better refrigerant. It just does more work. That's why you have smaller line sizes on the liquid. Doesn't take as much to do the same amount of work. However, there is a trade-off. The components, they're more robust. They cost more to build, so they cost more to buy. So there is absolutely an initial cost increase for a CO2 system versus an HFC. And then as far as the additional components to do the same amount of work, CO2 is eventually going to be regulated into your stores. Just to note, like in the countries in the European Union, just the European Union of Nations, there's 43,000 CO2 systems. A lot of those transcritical. In the U.S., we've got like less than 1,000. I think there's 900 and something. Canada has 600, so we're literally 1,500 for all of North America. So I know it's tough to spend the money on something, certainly if you're not buying the climate change or whatnot, but it is coming. The time to get familiar with it is here. The time to start specifying it is here. The last part of that question about the cost of the refrigerant, it's very cheap compared to HFCs. I want to say it's $100 a cylinder, something like that. So I hope that answers your question. And I don't know if we have any other questions. Okay, is there any plan to be able to program the pack controller through the 880 controller? That's a great question. And if I can get Josh for a close-up, I'll show you. So it's already included is the answer. One of these is turned on. Let me sign in real quickly. My apologies for not already being prepared. So this is the 880A that was referenced in the question. So the pack controller is already tied into this. Kind of the ecosystem for a store would be system manager, pack controller doing the system, and this governing the cases. The case controllers out in the store. But the high pressure control is already in the pack controller. So I can look here and see what it's doing. I can override the valve positions. I can do most of the things set point wise that I would need to do. This is our receiver control. So that functionality is already in the SM800. We've got our medium temp compressor shown here. There is also for the pack controller, if we come down one, there's also a remote display. We have a wonderful, easy to remember model number of MMIGRS2 for some reason. But this remote display, it will let you see the I/O for the pack controller. The system manager isn't meant for setup and configuration. It's meant for visibility and remote access to the pack controller. So you can't do anything with inputs and outputs here other than override some functions like compressors and fans and valve percentages. If you use our MMI remote display, it gives you full access to the pack controller, but it's a small display. It takes some getting used to. And then we have a software called Service Tool where you connect directly to the pack controller. So the interaction and the ability to make changes really is kind of good, better, best, with SM800A being good. This, as far as accessibility, better than the accessibility this will give you. And then the best would be our Service Tool software. I hope that answered the question. Do we have further questions? Oh, okay. So is there a class for how to operate the pack controller, specifically to how to navigate the controller and what data it displays means? So yes, I'm actually this week out doing training with pack controllers. We've got a pack controller training module you set on your desk, the desk in front of you. You plug your laptop into it. We load the software. We configure one. We go through the wiring, the issues at startup. We have a full day class specifically geared on CO2 and pack controllers. I think this particular unit is going to be here for a couple of weeks. It's going to the NASRC Summit in St. Louis. Then I believe it's either out of the country or out of our hands from there. But if you would like individual pack controller training, please get in touch with whoever your local sales rep is. Let us know, and we'll put something together. We would love to spend that time with you. So we have a question. Can this pack controller be used with a lower model Danfoss controller? If the question is in and around, do you need an 880? Like we have the 880 that kind of does everything, HVAC, lighting, energy. Then we have the 850, which I believe just gives you HVAC and refrigeration. And then the lower level, the answer is it will tie in and communicate with any of the models. Our base model is the refrigeration controller, so all the functionality is built into that. And then really what you're getting for the higher models is building control functionality and lighting control. Did I say that right, Chris? All right. So our next question, it says in CO2, redundancy seems very important to keep a system running and not blowing off lots of CO2. What would you recommend for the best places to include redundancy for safety, service, and maintenance? The best thing is a generator. I mean, if I'm not the one writing the check, I want a generator that'll run most of the store, enough lighting so people can still shop the store. If you wanted a cost-effective way, I believe it's underutilized in my opinion, but I believe the single condensing unit that's just meant to handle load in a power outage situation, because you've got the heat exchanger that'll deal with whatever pressure's built. It'll keep pressure from building in the flash tank, as well as it's a very small load to have a generator for. So I think a backup condensing unit with a small generator and a heat exchanger to keep the temperature of the flash tank from reaching the relief valves would be the best option. So it says, what are some of the most common service issues with CO2 systems? I can't really speak to the service issues. That's not really my forte. However, I can speak to the startup side, and I see people struggle with the oil. Everybody knows if there's an oil problem, you need to dump in 2 more gallons, or that's the common misconception. It's pretty common. People put in more oil than they should because the pressure switch wasn't defined correctly. There's some other issue, and they wind up having to take that oil back out of the system. So see some issues, people getting the oil portion right. And then service wise, I don't run service in that way. I kind of support startups and things like this. So I don't have a good answer, and I'd rather be honest. When we'll see mass adoption of the Danfoss mechanical TXV for CO2? It's available. I have one in a box inside this walk-in cooler. We already have the mechanical TXV. I personally struggle to see where that would be used, other than maybe like a C-store application, you know, box by box. And I'm assuming on that a small condensing unit with CO2 is still going to have some type of high pressure valve to give us liquid, but also to maintain just a limited amount of pressure on the TXV. But the mechanical TXV for CO2 exists today and is available. It is brought to you by Danfoss. Do you have any idea, any data on expected percentage of refrigerant loss per year on a CO2 system? I don't really have data on that. My guess would be the same people that put in the CO2 are the ones that put in the HFC. Whatever percentage leaks you see on the HFC, you probably see about the same on the CO2. Probably a fair guess. So we have a question asking about additional CO2 training at their actual training site. Chris, do you know if we have other training modules? We've got just food for thought. He's behind the scenes, but we have Chris Brown from Controller Talk Podcast. Chris Brown is here in the house. So I was through to him to ask if we have additional trainings. I do know that on our website, I can remember 15 years ago, you know, when CO2 were these large overfeed systems with liquid vapor separators. Most of the training that I did and the study I did was on Danfoss's website 15 years ago. If you go to our website and search for CO2 and learning, there are, I'm going to say, no less than 60 different presentations and modules to read through. So I would recommend our website. Okay, so that concludes our presentation. I want to thank you all for your time. Before I let you go, if you don't mind, I'd like to thank Raul, who is our engineer handling the audio visual, Maria and Josh from our marketing team, Chris Brown, who graced us. He is unbelievable wealth of knowledge. He's a hero to everyone that works here. So again, thank you for your time. I hope you found it useful, and we will put in the YouTube channel recording a link to where you can get the presentation from. And just because I'm childish and it's our motto, I wanted to, before I say goodbye, let you know that at Danfoss, we're engineering tomorrow. Thank you.